And I think we're live. Okay. Welcome back to this afternoon. I hope you guys are well fed, well rested. If we have new people, please help yourself to pizza and coffee and cold coffee by now. So this is the fourth lecture in the series. The 0th lecture was on Monday. First lecture was on Wednesday. And then the third lecture was 9 o'clock, and the fourth lecture was, second lecture was 9 o'clock, and then the third lecture was 10:30. Today, so we're doing a review of signals and systems, and I'm sticking my neck out a little bit to be a little bit more precise about what we'll cover in this lecture. We'll start with linear time invariant systems. We'll review some convolutions. I'll do some simple convolution examples. I'm a big believer in convolutions, particularly for this course. The way I argue it is, I think in signals and systems you get this bias where that you think by moving to the frequency domain and multiplying you cheat the system and it's easier for you, and maybe that's the case for a particular problem, but it won't be the case for all problems. Some problems it'll be much easier just to stay in the time domain and do the convolution and crank through that stuff. So by thinking it that way, I'm not forcing you into something more difficult. What I'm just saying is take the easiest path, and sometimes the convolution, if you learn how to do it, will be the easiest path. The other thing is I point out, and this I do it rather snidely, snarkily, is that remember, once you've taken it into the frequency domain and multiply, you're in the frequency domain, and gosh darn it, if you need it in the time domain, you've got to do that inverse Fourier transform, which may or may not be easy, right? So there's reasons why I want to spend some time on some simple convolution examples. I have a feeling that once I do it, but particularly in the discrete time case, you'll be okay with it. I think the way the timing will work out is we'll just be able to start Fourier series as well, and then certainly this afternoon we'll do a really good job of Fourier series, and that should take us close to where we need to be. Well, by the end of the day. And tomorrow we'll get back into Fourier transforms and in the morning and modulations in the afternoon. So I'm guessing that we'll get well through chapters 2 and 3 by the end of the weekend, and even into a little chapter 4. By my read, the way I usually do it is that's going to get us also pretty close to the subject matter for test number 1. When I get back from my operation and back in the classroom on a regular basis, I'm going to spend a day or so reviewing yet again the material that I'm putting on these videotapes. I know you're bored of it already, but that's just to reduce the anxiety and the fear and to allow for some questions, get us back in the gear of mode of things. And then I'll wait for 2 weeks before we have the test. And so there's no rush to get to the first test other than your midterm grades. So if you'll relax about that, then I can relax, and we can all relax about it. And then we'll move on with more AM and more FM and PCM and noise and other impairments. Okay, so that's where we are. I want to take just another couple minutes and review the previous class just to get us in the mode again. It might be helpful for the people who are going to be watching this on video later on. So we started off looking at some of one of our favorite functions, which is a delta function, which is a fairly magical function because it's located at some point in time, but it has infinite precision. It has no pulse width, so it's a zero pulse, and it has infinite amplitude. So it's the ultimate singularity. It's the ultimate point source. It's the ultimate Big Bang, if you want to think of it that way. The initial condition kick that starts the entire universe, or at least a desk that's a string mass system that shakes. And this is a way of arguing why, where you can get any kind of lump, shorten it and make it higher, shorten it and make it higher, maintaining the same energy so that the area under the curve is equal to 1. And that's a way to get the delta function. Mathematically, delta function is 0, except where it is, which is infinite. But the integral is well behaved. And so if you want to work with delta functions, the trick is to turn everything into this integral. Okay? There's a question about what I mean by normalization. And so this integral of whatever pulse you start with may or may not be equal to 1. So if I want to turn that into a delta function, I have to evaluate the integral, find out what that factor is, and divide the original function by that factor so that I force the area under the curve to be normalized term of art, to 1. And that's the only thing that's what we mean by normalization. It's a term of art. So many mathematicians and physics and engineering folks use that. It's not. It's just a jargon. It's just jargon to say that we do the integration, we find out what the value is, and we divide by that value so that it's equal to 1. Okay. Almost as simple as that. There are a few issues where if you have to, there are some situations where the normalization may be a little tricky, like a charge, like a point source of charge. But the geometry of free space brings up a 4 pi. That's kind of an interesting number. And some people would argue that that's a little bit of a worst case. But I wouldn't make too much of a distinction about it right now. Okay. This learning how to do the integrals, the concept of a 0 minus and a 0 plus, just to window that delta function a little bit. 0 minus an epsilon, 0 plus an epsilon, allows us to take the product of an ft times a delta t. That's a modulation or a product or a collision or an overlap or whatever you want to phrase that, and we will in a variety of ways when we look at a multiplier chip. And then we get out the sifting property, a very famous property of the delta function, which basically says that the value of f of t times del of t integrated for over all time is the value of the function f of t wherever that delta function lives. So if it lives at 0, it's f of 0. If it lives at a capital T, it's a t. And of course, as was pointed out brilliantly by you guys, if I have a sum of these delta functions, each located a period capital T away from each other, a sampling period capital T away from each other, then what I'm left with is not a single point, but a set of points. A set of points that form a discrete time signal. And so that's an example of going from a continuous time signal to a discrete time signal. And in that vein, several of you during the break asked a very, very reasonable question, a very good question. The difference between a continuous time signal, a discrete time signal, and a digital signal. And we're going to get to that in great detail when we do pulse code modulation. This is you're basically asking what goes on in a chip called an analog to digital converter. So have most people heard at least what an A to D converter is? So I'm going to be very rough and schematic and sketch that out for you.
I have one. I have an analog to digital converter for my computer, so that if I have a new computer and it's and the older projector, so when I give presentations, I have to use the converter to use the old equipment.
Absolutely. So how many of you Skype? So when you have a microphone and you put your microphone into the audio jack of your computer, you're speaking analog. You're speaking analog. There's an analog signal that goes into your computer, but it's processed through the waves. When it goes through the internet, through the fiber optic channels that are the backbone of the internet, it's a digital signal. And so it's a stream of ones and zeros. And so the conversion from that is an A to D converter in your computer. It's also in your chip. They're everywhere. They are everywhere. And they're fairly easy to design as long as you're not greedy. And I'll show you what that means. Once you get greedy, then they're very hard to design and very hard to work with. So here's how I want to kind of look at this. And again, I label this digression. Or answering a question, okay? I love my digressions. So I've got an analog signal, f of t, and so and this is I'll just call it a voltage as t. The voltage is a function of time, and because that's what it is. It's just a voltage as a function of time, and this can be the voice that you speak into the microphone. It's analog all the way to it gets to your computer, and inside your computer is an A to D chip that's going to turn it into a digital representation. The first thing it does is the sifting property, which is why I dropped this in exactly at this place. And the sifting property samples the signal at even periods. And so I need those last 2 points together. And so now I have the sampled, sifted property, the sampled property of my signal, and these points here I'm going to call V, the voltage values, as a function of n. So now I've gone from the V of t to a V of n, that's the continuous time signal, to a discrete time signal. And people who really love acronyms will label those CT and DT signals. I don't think you should over-acronymize. I think you should, it's not that much longer to write everything out, and certainly there's a lot of confusion that goes along with it. This will be, this axis now becomes n. T goes to n. And here's maybe sample 1, sample 2, sample part 3, and this is n equals 1, n equals 2, n equals 3, and so on. And we can accumulate them, and we can take the differences of them. We can do rolling averages, which means I'll average these guys together, and then I'll average these guys together, and then I'll average these guys together. That's a low-pass filter with a short recovery time. I could take these 2 guys and average and subtract off the other ones. That's another rolling average. I can take this guy and I can weight these guys as 1/3 values or 1/2 values, so I can do the weighted average in that way. Say discrete time signal processing using difference equations, as we also talked about a couple lectures ago. All right, now the important thing to note is V of t is continuous in the time domain, and it's also continuous in the voltage domain, which means I can have any range of voltages I want, any range of voltages. It's continuous. When I sample it, I still have a continuous time signal in the y-axis. So this is continuous in V, discrete in time, n. So this is sort of halfway there. This is continuous. This is discrete in one axis, but it's continuous in the other axis. And it's not a digital signal. It's not a digital signal. So then what you do is you go through and you collect these values in buckets. Okay? You collect these values in buckets. And this bucket is very different from this bucket, is very different from this bucket, is very different from this bucket, is very different from this bucket. Okay? So now what you do is you say, in those buckets, I'm going to report out one voltage. And that one voltage is an approximation for all the continuous voltages that are inside that bucket. And so this blue dot here becomes a big red circle in my colorful notation.
Would that be an average of those voltages?
It could be the middle of it. It can be the middle of that range. It could be the low end of the range, or it could be the high end of the range, depending on how you want to do it. And there's some subtleties that we may or may not get into in terms of noise, different types of noises that can. I will, since I brought up that word, this uncertainty is an uncertainty in the value, the precise value, and that's called a noise, and it's called a digitization noise. Okay? So I don't know. Before, theoretically, I knew what that voltage was to 20 different decimal places. Now I only know it to 2 decimal places, or 3, or 1, or however expensive, however cheap or lavish I am at the expense of that A to D converter. Okay? Typically 12 bits are reasonably inexpensive A to Ds. 16 bits are very expensive A to Ds. Okay? And costs are not just chip costs, gate costs, but implementation and putting them on the darn board costs. And we'll get through. We'll talk about all that as we go down. Just say that to summarize, the more significant digits I have, the more expensive I got to pay. Okay? It's the more precise. So sometimes it pays to be a little sloppy. You guys have heard, MP3 as a standard for audio. There are other standards that are much more high definition music. And those much more high definition music it means that these bins. One of the things is that these bins are much smaller, and so you take much more data to represent the waveform. Now if I have this, Now if I have this, let me give you a quick example. Maybe this guy here is 1.0273 volts, and I'm labeling that as, say, 1 volt. Okay? And so I'm truncating a lot of extra decimal places when I do that. And then further, what I'm going to do is, let's just say that I have enough precision here that I can, or I have sloppy precision, and I can represent it as a digital code. And I'll talk about 2 to the 3 or an 8-bit code. Okay. So that means I have a 1 or a 0 in 3 places, in 3 significant digits. So maybe this guy here, so I'll have a 0, 0, 0, a 0, 0, 1, a 0, 1, 0, a 0, 1, 1, a 1, 0, 0, a 1, 0, 1, a 1, 1, 0, and a 1, 1, 1. And that's 1, 2, 3, 4, 5, 6, 7, 8, 2 to the 3, 8 different things. So choice of 2, choice of 2, choice of 2, 2 times 2 times 2 is equal to 8. This is a bit and this is a word for my thing. And so now what I'll do is I can label this guy here as 1 volt, and maybe that's this guy here. So I have 1, 2, 3, 4, 5, 6 words that I've got to fill out. 1, 2, 3, 4, 5, 6 words that I've got to fill out. This guy here might be a 0, 1, 0. This guy here is the next bin up, so it may or may not make sense to do a 0, 1, 1. Another subtlety that we'll talk about later on down the line. The next one is the next one up, so that'll be a 1, 0, 0. The next one up will be a 1, 0, 1 in this silly case. So where am I now? I'm up to this guy here, right? Now notice that these 2 guys here are 2 very different values of voltages, but they wind up in the same bin. So that's a 1, 1, 0 and a 1, 1, 0. So even though I look at this graph and I say that ain't equal to that, well, once I do this quantization, once I do the quantization of breaking these up into buckets, into bins, I can't tell the difference between this bit and this bit. They're the same voltage. I've truncated my precision so that they're the same. I don't care about that. I'm saying in my design that I don't care about the difference between that, or I can't afford to care about the difference between those 2. And remember, it's not necessarily good engineering to do the most expensive solution. Right? So good engineering is also good trade-off of value. And so if these are good enough, maybe our ear can't distinguish them. Who cares? I'll point out, in the context of communications, that these are moderate levels of speech. These are loud levels of speech. And let's say, if I speak to you reasonably. Apparently I didn't do that with a police officer this morning, but if I speak to you reasonably, you're more apt to listen to me. If I'm yelling, it really doesn't matter what I'm saying, because you know I'm yelling, and the most lesson is that I'm yelling at you, and we don't really care what the details of what I'm yelling, other than only the fact that we're yelling. And so if I'm yelling you at this level, or I'm yelling at you at this level, just round it off to be a yell. Okay? It's important to note that compression or that bucketing can happen even down here as well. But in that case, there's judgment calls that you can do. One of the things we'll learn about is, in fact, we'll make these guys much smaller bins than these guys up here for exactly that reason. If we have only 8 samples to distribute, we may distribute them, 6 in this region and 2 in this region, even though they cover the same voltage. But we'll do that in a fancy way so that we don't cater to those jerks that yell into our telephone. Okay. So this guy here, if the original black line is the continuous time signal, and the next blue line is the discrete time signal, once I quantize and assign a digital code to it, then and only then do I have a digital signal. Okay? That's the roadmap in one small little lecture. and one little card on how you go from continuous to discrete to digital. Okay? Anyway, I got asked to that twice, and so I wanted to make sure that we covered that. Okay.
So is analog always continuous?
So an analog is working with the original curve. Okay. Discrete time signaling, that's a funny world. We'll do that from a computational perspective. We'll do that in a computational perspective, like on a computer, for example, or a calculator. We'll work in that road. But deep down inside the computer, it's working with the digital level. Okay. So we're and of course, as you were talking about the older projectors, there you're starting with a digital file, and you want to go backwards to a discrete and then a continuous time file. And that's called a digital to analog conversion. Okay, so moving this way is analog to digital, moving this way is that way to that way is digital analog. One person asked me a follow-up question, which I thought was also very good, which was, and it reminded me to write the IV curve of a transistor. And so I don't care if it's a BJT or a FET transistor. Okay, so looking at the IV curve, looking at something like this. I'm going to get in trouble by my devices, friends. Not that they're going to see this, but here's my IV curves. And so if you're down in here, you've got no current, no voltage, so off. And up here, you've got a constant. You've got current drawing and a constant voltage, or a changing voltage, whatever voltage I draw. I'm latched onto an on. So moving from this point to this point, or this point to this point, is an on-off switch, a digital switch, and it really doesn't matter where along in this you are. You're just letting your gate is open or shut, your transistor is open or shut. That's digital. That's a digital process. One value. Okay. If you want to work with an analog signal, then you bias it to a Q point. You come in with a small voltage, wiggling around here, and what comes out what'll come out will be an amplified voltage, or an amplified current in that case. Okay, and so this going through the effort, and I think you've seen this in your circuits course, going through the effort of biasing your transistor and putting a small signal in and getting a bigger signal out. Linear amplification, that was a lot harder than working ones and zeros, ons and offs, right? So there's an example. Now, one of the trade-offs, so the trade-off is you're sloppy about your voltages here, and I've presented that as a negative. I've presented that as a problem. What I'd like to also offer you is that can be a really good thing. Okay, supposing do you guys know what a record is, as in record player? I have to ask, because how many have seen one? Wow, students of history. I love it. So maybe some people want to. Yeah, that's true. So what it is, that's continuous in all senses of the word. You've got one spiral in your record, and you have a needle, and the needle is riding in the spiral in the groove, and the needle is connected to a PZT, a piezoelectric crystal. So the pressure on that crystal produces a voltage by the nature of the crystal. And so as the needle goes through the groove, it traces out in time. Okay, and as it hits deviations on that groove, the deviation is encoded in there because of the music. The needle bounces up and down. And the needle bounces up and down and exerts more or less pressure on the PZT, which exerts more or less voltage on the PZT, which gives you your Grateful Dead songs. That's a band from another era. Still very relevant politically today, but that's a whole other story. So that's your analog. That's your analog source. Now, what happens is invariably you're listening to the Grateful Dead with your thing, and those of you who know that sometimes you're listening impaired to the Grateful Dead, and so you'll be a little sloppy with your record, and you'll get a thumbprint on it or so on. In which case your needle won't go quite as high or low as it needs to go, and so your analog quality is compromised. When you make a compact disc out of that record, you round off some of the highs and the lows, and you bend them together. You take a hit that way. But once you do that, you've encoded part of that signal into a 1. And if you have a little bit of an impairment on it, supposing you wanted to read a 5-volt signal, but you only read a 4.2-volt signal on that, you round that 4.2 up to a 5, and you register a 1. If you wanted to 0, but now you're reading a 0.5 volts, well, you round that down to a hard 0. So the impairment or the noise that you've induced by your thumbprint on both of these records, both the record and the CD, is now treated in very, very different ways. And so the thumbprint affects the digital much less than it affects the analog. And so there's this perfect reproduction or near perfect reproduction of digital signals is a startlingly robust process. It's really good. So instead of taking a press of a press of a press or a slowly degrading record, you have an approximation of it, but the approximation is so much more reliable than the original. It's so much more robust and reliable, and that's a trade-off that many of us would love to make all day long.
When you say you round it up or you round it down, how does it know to round up or down?
It doesn't. Right? Both of these voltages, you've lost the distinction between these voltages forever. Okay? So if this nuance is important to you, you've lost it. If it's not important to you, then you've replaced it with a reliability and an elegance of representation. So think about having a PDF file. Okay? If you have a PDF file and you send it to a printer on a Monday, you send it to a printer on a Tuesday, those copies will be virtually identical. If the Monday one if your printer was broken, it's okay. If it's fixed, it'll be nicer again, right? Whereas in the old days, what you would do is you'd print it once, or you type it once, and then you'd make a Xerox of it. And a Xerox of a Xerox of a Xerox of a Xerox of a Xerox introduces noise and noise and noise. The letters get blurred, they get faded, and there's spots that grow on them. So the amount of white space to the amount of dark space to white space ratio changes. So analog reproduction versus digital reproduction are drastically different. And so yeah, you're right. Some people like the richness of sound from the analog, and that's this guy here. And some people have the time, the energy, the money to treat those albums really, really nicely, and keep them in a nice storage center and use them only with gloves and with the most expensive record players. And some people, even those same people, when they go to a beach or they're on an airplane, they want that music and they're willing to suffer an approximation of it so that they have the portability and they have the reproduction of it. Digital to analog in 30 seconds. With 30 minutes, I guess. My digressions are getting longer. Maybe we won't get to Fourier series, which would be fine. Sifting property for sampling. Relationship to the step function. Introduction of a slightly variation called the signum function that Lati uses and goes into in chapter 2 quite nicely, and so you can take a look at that. Using the delta function to characterize linear time invariant systems, what it means to be linear. I challenged you on what it means to be linear, what it means to be time invariant. I warned you that in signals and systems, every system that you looked at was basically, you could basically say was linear time invariant, and here it's not going to be the case. And we're going to celebrate that and be excited by those knobs that we get to turn that we didn't get to turn before. The only two things a linear time invariant system can do to a sinusoid. I send in a sinusoid like a cosine. The only two things, it can change the amplitude and it can change the phase. So if I know what this linear time invariant system does to all these cosines, every single cosine, the set of A's and the set of P's, as a function of, the set of A's as a function of omega, the set of Phi's as a function of omega, I have a representation, a full representation of the LTI system. I can construct that with a signal generator that I set to scan from frequency to frequency to frequency to frequency, record the output to get the output voltage or the output phase. That's one way of getting that representation. Another way of getting that representation is to fire in a delta function. The delta function has all frequencies, and so whatever comes out in the time domain or the frequency domain gives me the full representation for what happens to each of those components, amplitude and phase. Okay? How do we know something's linear or nonlinear? I offered a nice experimental idea where if I have new frequency components, then I know I have a nonlinearity. Because the only thing that this can do, the only thing a linear time invariant system can do is keep the frequency the same, change its amplitude or phase. So a nonlinear system or a time varying system, either will do this, will shift this frequency to a new frequency, shift this frequency to a new frequency. And as soon as you see that from an experimental perspective, you know you have some sort of nonlinearity, and that's actually a really nice tool to see whether it's a linear time invariant system. It wouldn't occur to a full theoretician to think of it that way, but if you're hunting around in a lab and trying to understand whether this box of components is linear time or linear or not, this is a great way to do it. Okay? And what'll happen, and I talked about a speaker, what'll happen is you crank the voltage up on this, on the input, eventually you're going to generate new frequency components. Where we are now was, if delta of t of a linear time invariant system gives you h of t, or del of n gives you h of n, how does that transfer? How does that translate to an x of t coming in to give a y of t if I know h of t? And if I send in an x of n and I know h of n, how do I get y of n? That's where we are almost or more or less at the start of this lecture. Okay? So, now, I'm going to start digital. Or discrete time, I should say. I'm sorry. All that long preamble, and I take a giant step back and confusing you guys. Now, if x of n comes into the system, h of n is the system response to one of those delta functions, and y of n is what comes out. Okay? So x of n is a set of samples. I won't do much with this waveform, but I'll just represent an arbitrary x of n. If I zero in on one of these guys here, let me emphasize that this is a linear time invariant system. If I zero in on one of these n's, one of these guys here, this is a delta function. It's been scaled in height, but it's still a delta function. And so the output of this guy here, the output due to this spike here, will be h of n, and because it's linear, it will scale to whatever value that is. So if that is half of a delta function, then what I'll get out is the delta function response scaled, each of those outputs scaled by a half. So let's supposing that the output here is just a decay. A big one, a middle one, a small one, and a nothing. Then this guy here will produce that train of outputs, and it'll be scaled proportional. So if this guy is an alpha, then this guy will be alpha times h of 0. Okay? I'll label that as 0. It's important that this is 1, this is 2, this is 3, and this is 4 in n. So it's important that this guy here, this output here, lasts longer than the delta function. So when the kick comes, the first kick comes, the system is ringing or bouncing around, it's responding longer than the kick. I don't give it time to recover fully. If these guys weren't here, then 0, 1, 2, 3, 4, 0, 1, 2, 3, 4, somewhere out over here, I'd have the reverse response. See, this is minus alpha, and this would be like that. So if I didn't have these guys in the center, this would fully recite. This would ring down. I'd wait for a count. A new kick would come, and it would ring down, except inverted. But what's happening with these guys here? What's happening with those pulses there? Oh, let me argue one more point. Looking at this set and looking at this set. The reason I was able to draw this so nicely is because the system is not only linear, but it's time invariant. So the response, when I got around to this 0, 1, 2, 3, fourth time point, it was the same system. And so the response was exactly the same. The only thing different was the minus sign, because this is now negative versus positive. Okay? So the linearity and time invariance here means that I get the same response scaled by a minus 1, and it just comes out there. So the system hasn't changed between the start of the signal and that signal there. But now I come in with these guys here, and I crowd the problem. At time point 1 in 1, I have the second breath of the system, plus I have the first breath from that guy. And then I have the second breath and the third breath from that guy coming in. And then at the fourth one, at the second one, I've got yet another one, and so on and so forth. And so for every one of these delta function kicks, I'm getting a delta function response. Shifted in scale, shifted in time. Shifted in scale, shifted in time. Superposition. Because of linearity and because of time invariance, linearity means I can add them together. Time invariance means I can shift them in position and time. Superposition. Okay? I can write this, and I'm going to be general about the formula. Y of n is equal to x of n convoluted with h of n, and that's equal to the sum from k equals minus infinity to infinity, so k becomes a dummy variable of counting. And it's going to be x of k, wherever that delta function lines up. And then the output is going to be h delivered, delayed by a k. So the superposition of this guy and this guy, this guy, this guy, and this guy are represented by that summation. So k is going to go from 0 to 1 to 2 to 3 to 4 and so on down the line.
And then CT, that would equal...
Sure. And yeah. So if you remember the sum, or the low pass, the sum, was sum of a discrete time signal was an integral for a continuous time signal. So you're absolutely right. And I'll get to that in a second. Unless you'd like me to do it now, but in fact, yeah, why not? And I'll present it exactly that way. I'll present it exactly the way you had it. I now go to a continuous time signal. I have x of t. I have y of t. It's the same issue, except now my delta function is a little bit fuzzy because I've got an infinite number of these delta functions. So this summation here, do you remember the Riemann sum? So do you remember to get from the Riemann sum of discrete bins and from calculus, you let those bins get smaller and smaller and smaller, you get a perfect. This summation becomes an integral, and you should have done that. You should have done that construction in signal systems. Well, depending on who your professor was. So y of t in this case is x of t convoluted with h of t, and this is equal to the integral. And the dummy variable of integration is tau in my notation here. X of tau, h of t minus tau, d tau. Okay? So the tau represents the shifting. So the location of the signal at the tau. Every tau gives me a delta function response at that tau. But the only thing is, in the discrete time case, I shift over a unit. Here I shift over an epsilon, a differential unit. So d tau versus a 1 here. Okay? I'm not sure I know how to spell Riemann, so I'm just going to be sloppy. Okay? Convolution. Okay? All right, so I think it makes sense to do an example. And I think it makes sense to do a careful example with discrete time case, just so we see that here. So I'm going to write h of n. And 3, 2, 1, 0. So maybe I'm doing the same problem, but I'm doing it in a little bit more, careful way. So you can look at this as a very bad approximation to a decay. You can look at that as a very bad approximation to a decay, say an exponential decay, say the discharging of a capacitor. Okay? So you can. I'm not saying you should, but you could think about that. I guess if I had to say something else about this, this is a finite impulse response. It's a finite impulse response. In other words, the one kick, comes in and only gives me an output for a certain duration of time. Okay. If this were a real exponential and I had no noise, then that would be an infinite response. It would go all the way out. Okay? If I have feedback in my system, that single pulse gets fed back again and again and again so that I have an infinite output. So we can make a distinction of systems, whether they're finite impulse response or infinite impulse response, based on whether or not we have an energy signal or a power signal, whether or not we have a finite train or an infinite train of pulses that come out. Okay, FIR versus IIR filters. I'll come back to that. Maybe. Probably will. I don't know how much I'll get into the details. That's sort of casual. Okay. The other thing to point out about this is, and you've seen this, the distinction between what the signal is and the distinction between what the signal is and what the response is blurs, because this is also equal to h of n convoluted with x of n. If I do a variable substitution, n minus k minus n goes there, and so I lose the distinction between what h of n is and what the input is. And that makes it easier from a calculation perspective, but it challenges you from a physical understanding. Okay, it challenges you from a physical understanding. So I bring that up just as a caveat. Okay, you should keep in mind what it means physically, and then do the math. That's the easiest, most straightforward, and know the fact that what you're doing. Well, the input that I'm going to choose here is just a stream of a pulse. And I didn't plan ahead, so I need one more color. Zero, 1, 2, 3. And the reason I want to use colors here is, as you can imagine, is I'm going to give you the impulse response to the first one, the impulse response to the red one, the impulse response to the blue one, and the impulse response to the green one shifted, and so you can see where the pulses are going to come from. I find that to be kind of nice for my own visualization as well. So the output, y of n, I have to draw this somewhat big. I bet I run out of paper on that side, so I'm going to have to be careful of that. 0, 1, 2, 3, 4, 5, 6, 7. Let's hope that's enough. I don't know. These heights, I'll just call these 1 to keep my life easier. Okay, they're all the same, and I'll talk to you a little bit about that as we go along. So at times t equals 0, the first kick of 1 comes in, and I get an output that's 3. Then I get an output of 2. Then I get an output of 1, and then I get an output of 0 forever. Okay. Is this a physical system? Is there something wrong with this system? I come in with a single unit of energy in, and that single unit gives me a 3, a 2, and a 1. What's the energy of my output? 3. If my energy in is 1, that's the height of this delta function. What's my energy output that I've drawn so far? What's my energy output of that signal there? It would be the energy in this pulse, plus the energy in this one, plus the energy in this one. So 3 plus 2 plus 1 is 6. So I've got a system where I bring in 1 piece of energy and I get 6 out. That means if I have a bank where I give $1 in and they give me $6 out, I'm liking that bank, right? Usually it works the other way around.
Did you not square each of them when you're calculating energy?
I could, yeah. I should. I absolutely should. So I have 1 unit in and I have 9 plus 4 plus 1 coming out. Okay? Yeah, it's a good point. And that's assuming that these are voltages and not energies to begin with. Okay? So yeah, so I'm getting more energy out than in. So the only way I can imagine that to happen is if I've got a battery or a power supply hooked up to that. So I feed energy in from some other wall socket or a battery so that I get more energy out that I put in. And that's possible. Okay. One thing that's nice about this is I bring a pulse at 0, and the output starts coming at 0. So we can call that a causal system. We can call that a causal system. Okay? Non-conservative is a fancy $10 word that means it has 10 units of energy out for 1 unit of energy in. And the causal system means that it doesn't start before the kick happens. Okay? Usually the poor person that's sitting right there, they start to flinch after I've kicked the desk 40,000 times in my illustrations. And so you can see the person flinch before I actually kick it. And by that time, that's a great demonstration of a non-causal system. Because that person is anticipating the kick before I even kick that desk. In this case, the desk itself isn't going to flinch because it's a dumb, passive system that it just sits there, right? And so physical systems that are generally usually causal. They don't start before they get hit. Okay. All right. So back to my example. I've just traced the first pulse in, and I now know what the output is. I wait a beat, and the next unit comes in. I've drawn this in a boring way, so it's a 1. If it was a -1, I'd flip it this way. If it was a positive 7, I'd get 7 units times 3 out. But it's just a 1-to-1, so I get this one here gives me a 3-2-1 response, but it's causal, so it starts at 1. So add to the 2, I get a 3. Add to the 1, I get a 2. Add to the 0, I get a 1. And so the output here is a 3, the output here is a 2, and 2 plus a 3, and I'm not done with this guy yet. All this is a convolution. Wait, W-E-I-G-H-T, and shift. Wait and shift, wait and shift, wait and shift. I'm just accumulating the response. Okay? Take another step in time to 2. I get a 3-2-1 response, but now it has to start at 2 because this kick started at 2. So I get a 3, I get a 2, and I get a 1, and I get a 0. Finally, the green pulse comes in at 3. I get a 3, I get a 2, I get a 1, I get a 0. The inputs stop coming, the outputs stop coming after 6. The final 3, the final pulse came at 3. I still relax, the system still relaxes through 4 or 5 before it's fully relaxed. The pulses that come in the middle, the 1 and the 2 and the 3, they're seeing the trailing edge of the pulses that came before it. So the response is that much bigger. So the final answer for this is a 3, a 5, a 6, a 6, a 3, and a 1. Okay? Simple graphical expression for what we're doing. It is all bookkeeping. And it's all directly related to what's the physics of the collision, the physics of the excitation. Okay? I bring in a kick, I get a response. I bring in another kick, I get a response, but the other response hasn't finished, so I've got more excursions. If I start to play with these, shift these to be negative, well, if this red was negative, then I would start here and I'd go down 3, 2, 1, and I'd subtract a 2 minus a 3, a 1 minus a 2, and so on. Okay? So that's, and then if this were a 12, then instead of the 3, I'd have a 12 times 3, or 36. It's just scale and weight, W-E-I-G-H-T. No, W-A-I-T in that case. Oh well, let you figure that out. All right. So here's my convolution of a square pulse with a decay, and you see that it piles up and then it comes back down again. Okay. Let me show you a different way to bookkeep. Okay. Let me show you a different way to bookkeep. I'll try not to make too many mistakes here. H of n is I can draw a table, by the way. I can draw a table, and you might want to code this up in Excel and then list the tables. But I'm going to show you it. I'm going to show the cells by delta functions. So the H of n is 3 del of n plus 2 del of n. Is it minus 1? Thank you. Plus 1 del of n minus 2. Okay. So y of n will equal 3 del of n plus 2 del of n minus 1 plus 1 del of n minus 2. That's from the first pulse. From the second pulse, the second pulse is a 3, 2, 1, but it starts here. So plus 3 del of n minus 1 plus 2 del of n minus 2 plus 3 del of n minus 3. I am going to run out of paper. Oh well. That's life. So now I'm at the graphical equivalent of the black and the red traces. I now come in with the blue pulse, which happens at 2. So that's going to be a 3 del of n minus 2 plus a 2 del of n minus 3 plus a 1 del of n minus 4. Sure.
Your 3 del of n minus 3, is that, why is that 3?
Oh, you're right. It's just a mistake. It's just an error. Thank you. No, it's just a silly mistake. My bookkeeping was completely wrong. Thanks for that. I put that in there just to see if you guys were awake after lunch. Sometimes that works. So now I have accounted for all these pulses except for the green ones. And now I'll come in with the green pulse, and I get a 3, 2, 1, and it starts at 3. So that's a 3 del of n minus 3 plus a 2 del of n minus 4. And I'll just squeeze it in here, a del of n minus 5. Horrible. Ugly, ugly, ugly. Sorry about that. And now I add 3 of del of n plus 5 of del of n minus 1 plus I got confused. 6 of del of n minus 2 plus 6 del of n minus 3 plus 3 del of n minus 4 plus 5 plus 1 of del of n minus 5. Okay. So that's a more formal bookkeeping approach to what we were doing, but it's still summing and shifting, summing and shifting, summing and shifting. And you can see if I now get rid of the delta functions, and this is just on a spreadsheet, you can see how that's just going to accumulate. Okay, gives you an idea on how to code this both in MATLAB and also in Excel. I'll also give you and please take this back to the other section of 3350. If you go to my webpage, which is www.utdallas.edu/DLM, or approximately signed DLM, I'm approximately a person. Those are approximately my initials. Then you'll find a signal. Then you'll find a Comm Systems link on that page. Go to the Comm Systems link. Scroll to the bottom. And what you'll find are all the MATLAB code from chapters 2, 3, 4, 5, 7, and so on. And they're either in the .m files or in a text file. And so you can open those up, cut and paste them into your MATLAB, and it'll show you how to do convolutions. It'll show you how to plot signals. It'll show you how to do FFTs. It's just there. And you can go in there and you can change it. It's the same code that's in your Lati book. But I understand there's a big, it's kind of a drag to type it all in. And so over the years, we've paid TAs to do that, and so they've been very gracious to do that for us. And so you have access to all that. And I think that's such a nice and simple way to get to know this code. And if I were you, I would steal that. And I would start a library of .m files, and I'd play with them. Particularly when we get into AM and FM, all that stuff is there. And then and by the way, if you're not an expert in MATLAB, or if you've never started MATLAB, there are 3 or 4 lectures from 3 or 4 other TAs that talk you through various aspects of getting started with MATLAB. So in the old days, what would happen was when I would go on travel and we didn't have this lavish system, then I would ask my TA to come in and give a lecture. And since I was never really sure in the semester when that was going to be, I just asked the TA to lecture on something that they knew, which was how to use MATLAB. And so they would generate a set of slides, and they would give that lecture on how to use MATLAB, right down from this is how you open up a window in it, this is how you plot something in it, and this is how you do it FFT. And so they recorded, they put all that stuff into, and it's a great resource. So if you've never worked with MATLAB before, open one of these PowerPoints and just follow along. And then you've got the code, and you've got the examples, and you've got all this stuff, and I'm not saying you're going to be an expert in MATLAB, but you're sure as heck going to know the basics of it. And you're going to get over that curve of, I'm afraid of MATLAB, and now to the point where now I can use it. And so I really think that's a great resource for you guys who want to, and you should want to do this in MATLAB. I will also point out one other thing, and that is, you may not have access to MATLAB. MATLAB is a fairly expensive program. So you may not have access to MATLAB. And so there's two alternatives for that. One is there's an open source MATLAB. And for the life of me, today standing up in front of you, I cannot remember the name of that.
Octave.
What is it?
Octave, yeah.
Octave, thank you. So Octave is a open source software that is almost identical to MATLAB, but it's not. So there's a little bit of perversions back and forth. But other than that, but the advantage of it is if you know Octave, you're not relying on somebody else's thousands of dollars for all the MATLAB toolbox. So, geez, I don't know, if I were starting out, I wouldn't want to be tethered to an expensive, royalty license. I would want to contribute to the open source software and republish everything that I do and go that route. I also have noticed before Octave came out, really take a look at this kind of stuff here. Excel. Excel is very, very, very powerful, and there's open source versions of spreadsheets as well. And so even Excel, you may not know this, but Excel can do FFTs. So if you have a stream of numbers you import it into Excel, you can take the FFT of it. In fact, before MATLAB and before LabVIEW got big, I worked at TI, and I was running an experiment I designed the illumination system for the projector displays that use the DLP. And a lot of the stuff that we came up with are still in the boxes, integrating tubes and tubes and so on. But in the experiment, it was so funny because everything was computer controlled without LabVIEW, and so everything actually went through a quick basic, and into Excel. So the plotting of the oscilloscope trace was a plot in Excel. And TI was big enough that they were able to support 6-8 techs that were so expert in Excel and interfacing Excel to equipment that they had their own internal software development team to do Excel interfaces to all the instruments, and they didn't have to worry about whether or not LabVIEW came up or didn't come up. They had that control system already. Really interesting. We had a problem in this. The IT guy came right in there and programmed in Quick Basic, QB, Visual Basic, and so it just went right in there and coded it up and got that particular oscilloscope online with the experiment. Very impressive, but gives you an idea of how to do that. All right, that's the discrete time case, and I think it's really useful to start with the discrete time case because I can't emphasize enough just how robust that is and how physical that convolution is. And if you guys are afraid of convolutions, remember that most of the time you're going to be working in MATLAB, which is an accumulation anyway, and here's your physical interpretation of it. Okay? One more thing to say about that. And I haven't practiced this, so I may get this wrong. But you will remember that what you're supposed to do is you're supposed to flip these and walk these through. Right? So let me just try to do that for you. No guarantees because I haven't practiced this, so I may be off. But you guys can check me on this, right? So if I have a 3, a 2, first be neat. If I've got a 3, a 2, and a 1, and then I've got a 1, a 1, a 1, and a 1. So you see what I've done is I've flipped, and now I'm walking through. This is the I won't go into the details of that, but some people interpret this minus sign here as the flipping function that you want to do. And you'll notice that I'm being a little bit, I'm actually doing this problem here. So I've chosen to flip the input signal and walk that through. Okay? So now what you do is you multiply, 3, 2, 1, and add. And so this first one here is a 3. So I have a delta, I have 3 delta, and that occurs at n. Okay? So the next line is a 2. Oh, thank you. Is that better? A 1. A blue, and a green. So now I have a 1 times a 3. And I've got a 1 times a 2. And that gives me a 5 del at n minus 1. Just to show you I'm on the right track, I haven't made a mistake on this one, and I haven't made a mistake on that one yet. Okay? So this method seems to be working pretty well. Let me keep going with this. Redraw the 3, the 2, and the 1. I shift my input over one more. So let me make sure I'm pleased the 3, the 2, and the 1. I have the black one should be lined up here. The red one lined up here. Is that right? And I need your help on this. The blue one here, and then the green is off the map still, right? So now I multiply and I sum. So that's a 3. 1 times 3 is 3. 1 times 2 is 2. 1 times 1 is a 1. So my next one will be I will have I'm looking at delta of n minus 2. So my first one here would be a 3 times delta of n minus 2. That's what I have when I get multiply this by this. I add to that a 1 times a 2, which is a 2 at delta of n minus 2. That's my bookkeeping register. And then I add to that a 1 times a 1 plus a 1 delta of n minus 2. And that's a 3 plus 2 plus 1, or that's a 6 delta of n minus 2. And thanks to your help, I was able to get that one okay. All right? And so now we shift through again. And I've got the black one has cleared the system. The red one is at its last response. The blue one is still smack in the middle. And the green one has just entered the system. Multiply, 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 add. So the green one gives me a 3 delta of n minus, thank you. The blue one, help me out. This one multiplied by that one, good. Where is it? I'm stuck at n minus 3, so that's that's good. Where am I now? The red one? Plus 1 delta of n minus 3. And I get the 1 because I multiply 1 by 1. And I'm adding because of that summation, the summation here. Right? And if I add all these guys up together, that's equal to 6 del of n minus 3. I should have 2 more cases, I think. 5 minutes to go, so I might as well do that. 3, 2, 1, 3, 2, 1, and n equals 4. Here's my signal. Let's see. 0, 1, 2, 3, 4, 5. My black one is sitting out. Yeah, I think my black one is sitting out here at 4. My red one is sitting out at 3. My blue one is sitting out at 2. And my green one is sitting out at 1. I think I did that right. Did I do that right? For the n equals 4 case? So now I multiply and I add. So at n equals 4, I'm looking for terms at d of n minus 4. I've got a 1 times a 2, which is a 2. I've got the blue contribution, which is a 1 plus 1 times a 1. And that occurs at the n minus 4 case. And the red and the black are off the map. And so that's equal to 3 del of n minus 4. Again, the same bookkeeping that we had before. Let me know if you need to review that, but if I can flash that up. The final one is the n equals 5 case. And the black one is now moved off to the 5 location. The red one is now at the 4 location. The blue one is now off the map at the 3 location. And the green one is on its last interrogation of the system. So this is particularly easy. 1 times 1 is 1. 1 del of n minus 5 plus nothing else equals 1 del at n minus 5. Now I just have to be somewhat good at remembering what I have. So I have a 3 del of n. And this is y of n. I'm just going to write down all of it. So the first term is 3 del of n. The second term is 5 del of n minus 1 plus 5 del of n minus 1. Dig up my old piece of paper for the n minus 2 case, and I've got 6 del of n minus 2. 2 more minutes. 6 del of n minus 3. And now I'm on this page. 3 del of n minus 4 for the n minus 4 case. And finally, plus 1 del of n minus 5. Okay? So the trick of flipping and walking through works just fine for the discrete time case as well. And next time, in 15 minutes, I'll start with that. I'll start with the continuous time example. And what I'll do actually is a square pulse with an exponential decay. Or maybe just a linear decay. I can't remember which one I picked. But we'll walk through this basically the same problem in continuous time case. And there we'll use the flip and shift method. Okay? Let's take a 15-minute break. If you're hungry, thirsty, help yourself. And we'll come back in just a little bit.